Right. Question 11. Now, again, I can't remember where I took this question from, but it's one of the more recent papers. And the reason why I really want to look at this question is because it's with a graph. And graphs are really, really important. So, they tell you a learner is investigating the photoelectric effect for two different metals, silver and sodium, using light of different frequencies. The maximum kinetic energy of the emitted photons is plotted against the frequency of the light for each of the metals as shown. Now, when this kinetic energy is 0, we get a frequency for each of these, and this is times 10 to the 14. This is the threshold frequency for sodium and silver, because the kinetic energy is 0. So the first thing they ask is, what is the threshold frequency? So we've done this lots now, but we'll just do it again, because it's important to do these things over and over and over again. Alright, so it is the minimum frequency of light needed to eject electrons from the surface of a metal. Okay? Which metal, sodium or silver, has the larger work function? Well, work function is directly related to threshold frequency. So whichever one has the bigger threshold frequency has the greater work function. So if we look at this and we go, well, silver has the biggest threshold, so it's going to be silver. Ooh, silver. Why? The threshold frequency of silver is bigger. And since WO equals HFO, WO will be greater or larger, either way. Okay? Then, name the physical constant represented by the slope of the graphs. And this is quite a complicated one to get around, but essentially it's Planck's constant. Okay, that's the gradient of the graph. If you turn the graph into a y equals mx plus c equation, where m obviously is your gradient. If light of the same frequency is shone on each of the metals, in which metal will the ejected photoelectrons have a larger maximum kinetic energy? Sodium. Why? Because sodium has the smaller work function. And remember, when you're looking at the maximum kinetic energy, okay, E equals WO plus EK max. Okay, now they didn't ask you to explain it, but I want you to see it. This is the same for sodium or silver, because it's the same light. This is what's different. So if for sodium this is smaller, EK must get bigger, so that we have the same total energy of the photons. Okay? Then, in a different photoelectric experiment, blue light obtained from a light bulb is shone onto a metal plate, and electrons are released. The wavelength of blue light is 470 times 10 to the minus 9 at a rate of 60 milliwatts. Okay? They tell you the bulb is only 5% efficient. Calculate the number of photons that will be incident on the metal plate per second, assuming all the light bulb from the bulb, all the light from the bulb is incident on the metal plate. Now this one is a difficult question. Okay, we have a power of 60 milliwatts times 10 to the minus 3. Okay, we divide by 1,000. Of that, only 5% of the light that's produced, or of the efficiency, so 5% of the energy that goes into the light bulb actually creates light that we can use. Alright? So, when we look at this, now we're going to look at this very carefully. Okay? Is my energy of my blue light, or the power, is going to be 60 times 10 to the minus 3, times 5 over 100. So this energy in terms of rate, okay, in fact, no, I'm going to put this as power. I think it's a better way to do it. Okay, of the blue light is 3 times 10 to the minus 3 joules per second. Alright, so the power, the rating, is that we have 3 times 10 to the minus 3 times 10 to the minus 3 joules per second. Now, the energy of our photon, and we're looking at blue light, which has a wavelength of 470. So if this was 100% efficient, we should have this amount of energy, okay? So we have 3 times 10 to the 8. This is 470 times 10 to the minus 9. And this gives me 4,232 times 10 to the minus 19 joules. Okay? Now, this is how many joules per second hits my my metal. This is the energy of one photon. Okay? So the number of electrons is going to be the total amount of energy per second that hits my metal divided by the energy of one photon. Okay? That's going to give me 7,09 times 10 to the 15. This is the difficult part. Okay? You're going to need to think about that again. So we worked out the total amount of energy that the photons give to the metal. Then we worked out the energy of a single photon, and we divided it by that. Okay, and that gives us the number. Photons are incredibly small, so I expect it to be an incredibly large number.